history, there have been many great discoveries leading to several advancements in society. These discoveries have led to endless, infinite, and everlasting potential. When considering these terms, they can also be used in the world of mathematics to describe fractals, also known as the world's most beautiful chaos. Fractals are an object or pattern that represents self-similarity on all scales. To put into simpler terms, fractals are an object or pattern where no matter how broken down or magnified the object may be, it will still represent the same shape or pattern it would in its original magnification. Since the discovery of fractals, there have been two leading researchers that have helped continue the trend and encourage research in the future. One of them being Benoit Mandelbrot. Benoit Mandelbrot was born in the early 20th century, and he was the creator of the Mandelbrot set, which is shown by this recursive formula here. One diagram, the Mandelbrot set, is here. Now, let's just say we picked any spot on this diagram, say right there, and we zoomed in a million times. It would still look the same exact way it would in its original form. Mandelbrot earned many achievements and awards for his great discovery, and most certainly encouraged future researchers. Another researcher in the world of fractals is Gaston Maurice Julia. He was the creator of the Julia set. The Julia set is shown in this formula here, and when broken down into a diagram, it is set along this axis right along in here. And again, if we picked any spot and zoomed in a million times, it would still represent the same exact shape it would in its original form, therefore satisfying a fractal. Besides the Mandelbrot set and Julia set, there are many other types of fractals that can be found in the world, one of them being the Koch snowflake. The Koch snowflake, when diagrammed, starts out in a simple polygon, but then follows a factor of 3. So then it would be branched off into 3 triangles instead of 1 in its original form. Then it would go into 9 and 27 and so on for an infinite amount of steps. Another type of fractal that is found in the world is the Sierpinski triangle. The Sierpinski triangle will start out in a regular equilateral triangle, but again, it will follow a factor of 3. So in its next step, it would be broken down into 3, then 9, 27, and so on. And this again can go on for an infinite amount of steps. Another type of fractal that is found in the world are spirals. Spirals follow a formula r equals e to the power of t times theta, where r equals the radius and theta equals the angle at which the spiral is set at. Spirals can be represented by this animation shown here. In nature, spirals can be found almost anywhere. You name it, there's a spiral in there. Spirals can be found in places such as galaxies, hurricanes, typhoons, cacti, flowers, pine cones, and believe it or not, shells. Let's say you're walking alongside a beach and you pick up a small shell. Little did you know that it is one of the most intricate and complex things in the world. Now that you know that a shell is a fractal, we must ask ourselves, what allows a shell to be a fractal? We have to consider its growth process and what it consists of. A shell is composed of 3 distinct layers, one being an uncalcified layer of proteinaceous periosteum, followed by a middle layer that is known as the prismatic layer, which is highly calcified. And it is then followed by a calcified pearly inner layer. When I say calcified, that means the hardness of the shell. Shells go through a process known as mnemonic growth, in which they grow in a constant factor. And they start at the edge of the mantle and continuously add new shells to its opening. And they grow from bottom to top. This process can be shown in this diagram shown here, where it will start out in its simple shape and continuously add new shells from its opening, therefore representing mnemonic growth. This can be shown in this shell here, where again it starts out in its small form and continuously added new shell and grew at a constant factor and formed this spiral. So now that we know how shells are formed and what are composed of them, we can consider the different types of shells. One being the spiral mirabilis. spiral mirabilis was first described by René Descartes in 1638, but it was given its official name by Jacob Bernoulli years later. The spiral mirabilis formula can be shown here, and when broken down into a mathematical diagram, it is represented here, representing mnemonic growth and growing at a constant factor. And when using this formula, the tangents and angle at which the spiral opens can be found. The type of spiral mirabilis shell that is found in nature is known as the nautilus shell. Another type of spiral that is found in nature is the equiangular spiral. This is closely associated with the spiral mirabilis, and it was first noted by Christopher Wren in the 17th century, but a clear mathematical model was not made until 1838 by Henry Moseley. The equiangular spiral formula can be shown here. In fact, this formula is equal to the spiral mirabilis formula, except this one just uses logarithms. When broken down into a mathematical diagram, the equiangular spiral can be represented here. Again, where tangents and the angle at which the spiral is formed at can be shown. There are many places where you can find an equiangular spiral in nature, one being in animal horns, or even something as small as a snail shell. Another type of spiral that I'm going to be talking about today is the helical spiral. This spiral proves how shells are three-dimensional. When broken down into a mathematical diagram, they can be represented here. This represents the mnemonic growth, and this diagram represents its three-dimensional surface. A type of shell that represents the helical spiral is known as the Japanese wonder shell, which is shown here. Again, representing mnemonic growth as it continuously grows, and its surface is three-dimensional. The last type of spiral I'm going to be talking to you about today is the Conco spiral. This type of spiral consists of a space curve with parametric equations, which are shown here. When the results of these parametric equations are positive, the torsion, curvature, and length can all be found here. When broken down into a mathematical diagram, the space curve can be shown here. A shell that represents this is shown here, again representing mnemonic growth as it continuously grows outward and adding new shells to its opening. In conclusion, spirals have been a great discovery in the world of fractals and have continuously encouraged researchers in the future, and there will be a great increase in knowledge in the world. Thank you.